Quadratic functions and their graphs. So we have a couple of learning targets here. Much of this should be reviews, maybe one or two new topics here. But you can see lots to do here in section 3.1. So to start, just a review, quadratic function, there's two forms. The general form is perhaps a little more common. You can see here, ax squared plus bx plus c. Most quadratic functions are given in general form. But when it comes to graphing, general form is not very useful if we wanted to graph a quadratic function. And remember, the graph of a quadratic function is a parabola. So what we do is consider the quadratic function in what's called standard form. Standard form is also known as vertex form because the vertex of the parabola, which if you remember, the vertex of the parabola is either the minimum value if it's facing up like this, or the vertex could also be the maximum value if the parabola were facing upside down. So the vertex has a coordinate location of h and k, and that location is embedded within the equation for the standard form of a quadratic function. And this is actually from section 2.6, transformations of functions. This moves the vertex left or right. This moves the vertex up or down. This transforms the parabola as a vertical compression or a vertical stretch. So this first learning target is taking a quadratic function that's in general form and writing it in standard form. So here's an example of what it would look like on your homework. We have been given the equation of a quadratic function in general form. We first need to express it in standard form, and then find all the x, y-intercepts, graph the function, state, domain, and range. So the technique is called completing the square. So for part A, use complete the square method. And let me get a little more room here. So there are certain quadratic expressions such as these. They're called trinomials because they have three terms. Trinomial means three terms, but they're a special type of trinomial called perfect square trinomial. They're called perfect square trinomials because when we factor these, they factor into two identical factors. So x squared plus 4x plus 4 is x plus 2 times x plus 2, or x plus 2 squared. X squared plus 6x plus 9 is x plus 3 times x plus 3, or x plus 3 squared. And it's really writing it in this form that's the key. This one here, x plus 4 times x plus 4 equals x plus 4 squared. So these are all examples of what are called perfect square trinomials. And the key for this topic that we're on right now, completing the square, is we want to form what are called perfect square trinomials, or we want to be able to make some of our own. And what often happens is that it's incomplete. For example, we have part of a trinomial, and the task here would be to add a number to this trinomial so that it becomes a perfect square trinomial. So what we need to do is, looking at these three that we've already done, recognize a pattern. Where is the pattern? What is the pattern? And particularly, what is the pattern between this number, and this number? Right here. What's the pattern? And the pattern is we need to find a number that multiplies to itself here and adds to itself here. So this 10, for example, if we split it in half, 10 is 5 plus 5. So then 5 times 5 would be 25. And there is a small formula if you're the type that like to use formulas or like to memorize formulas. If we consider our general form trinomial, ax squared plus bx plus c, then to form a perfect square trinomial, this value here is half of b squared, where this is b. So half of b would be 5. 5 squared is 25. Now that we've formed a perfect square trinomial, we have, quote unquote, completed the square, in which case we can write this as x plus 5 times x plus 5, or x plus 5 squared. So this is essentially what we're doing, is creating perfect square trinomials. So going back to our example here, we have f of x equals x squared minus 4x minus 5. Now, this is a trinomial, but it is not a perfect square trinomial. So what we need to do is change this trinomial so that it's a perfect square trinomial. The problem is this 5 right here. Shouldn't be a 5. So what we need to do is move that 5. So I'm going to add 5 to both sides of the equation. And now there's a blank spot where that minus 5 used to be. And this is where we do what we just barely did in that last example I was showing you. We create a value, or we add a value to this trinomial that quote unquote completes the square, makes it into a perfect square trinomial. So here we need to add half of b to the second power, where this is b, negative 4. Half of negative 4 is negative 2. Negative 2 squared is 4. So we add 4 to form a perfect square trinomial on that right side. Now, because this is an equation, if you add something to the right side of the equation, you have to add that exact same value to the left side of the equation to balance things out. So we have x squared plus 9 equals x squared minus 4x plus 4. And then we can factor this right side now in the same way that we factored all of these perfect square trinomials over there. x squared minus 4x plus 4 is x minus 2 times x minus 2, or simply x minus 2 squared. And then the very last step is to move this 9. So the function in standard form now becomes x minus 2 squared minus 9. And like I said, for the purposes of graphing quadratic functions, graphing a parabola, you're going to want the equation in this form, in standard form, because you can easily now find the vertex by following the transformations. So, well, and even though it doesn't explicitly say to state the vertex, we're going to use that anyway in part C when we graph the parabola, or part D. So the vertex, the graph has moved 2 units to the right and down 9 units. And so the vertex is the point 2, comma, negative 9. Now, part B, find all the intercepts. To find y-intercepts, you let all the x's equal 0. So to find the y-intercept of any function, not just quadratic functions, and this is something that I'll mention a few times in this course because we do a lot of graphing. To find y-intercept of any function, you let x equal 0. So if I let x equal 0, we get a y-intercept of negative 5. So the y-intercept is the point 0, negative 5. Now to find x-intercepts, and again this applies to any function, not just quadratic functions, you let y equal 0. And remember that f of x is really the same thing as y. So to find x-intercepts, you let y equal 0, or you set the function equal to 0. So 0 equals x minus 2 squared minus 9. And then you need to solve the equation. So one way you could solve this equation is to add 9 to both sides. And now you can square root both sides in order to cancel that square. So if you square root both sides, you're going to get plus or minus 3 is equal to x minus 2. And if you add 2 to both sides, you're adding 2 to positive 3 and you're adding 2 to negative 3. So you would get x equals 5 and x equals negative 1. So our two x-intercepts are 5, 0 and negative 1, 0. Now for part C, graphing the function, we have the vertex at 2, negative 9. We have 5, 0 and negative 1, 0, and then 0, negative 5 as our y-intercept. And finally, domain and range. The domain of any quadratic function is all real numbers. The range of a quadratic function has to do with the vertex. So the vertex is down here when y equals negative 9. So the range is from negative 9 to infinity. Okay, so we're going to try it again on our new example. Same thing, we're going to complete the square to write this in standard form. Right now it's given in general form. So it's going to start the same way. This 2 needs to move to the other side of the equation so I can add a value that will complete the square. So I need to add 2. Now this one's a little different because it has a leading coefficient that's not 1. So this next step, you want to factor out this leading coefficient of these two terms now. Factor out that leading coefficient from those two terms, because remember, this term is gone. We added it to the other side. So if I factor out a -3, that's going to leave me x squared minus 2x. And you only factor out the leading coefficient. You don't factor out the x. So if I factor out that leading coefficient of -3, you get x squared minus 2x. And I'm going to close the parenthesis a little further to the right, which will allow me to add a number into that trinomial inside the parenthesis that completes the square. And again, the value that is added there is half of b to the second power, where this now is the value of b that we use. So half of b is -1. -1 squared is +1. So I'm adding a +1 to complete the square. And here is where I see a very, very common mistake. So please listen carefully. I've just added a value to an equation, so I've made the equation unbalanced. So you need to add something to the left side to balance the equation out. But you have to think really carefully here. What was the value that is added to the right side of the equation? It looks like it's a +1, but it really isn't. If you were to distribute that -3 into the parenthesis, I've really added a -3 because -3 times 1 is -3. So the value that I have to add to the left side to balance this out is -3. Again, let me repeat that. It looks like I've added a +1, but if I were to distribute that -3 to get rid of the parenthesis, that +1 would turn into a -3. So I've really added a -3 to the right side, so I have to add a -3 to the left side to balance it out. So now I have f of x minus 1 equals -3. And then x squared minus 2x plus 1 is x minus 1 squared. And then if I want to finish this up, I move this -1 to the right side and get -3 times x minus 1 squared plus 1. So here is the function in standard form, vertex being, if I move to the right 1 and up 1, which is what those transformations are, the vertex would be the point 1, 1. And then the y and x-intercept. So the y-intercept, remember we let x equal 0. If you let x equal 0, we're going to get here -1 squared, which is 1. And then this 1 times -3 is -3. -3 plus 1 is -2. So it's the point 0, -2. Now x-intercept, we let y equal 0, and y is the same as f of x, so we set the function equal to 0. And try to solve this equation. So if we subtract 1, we get -1 equals -3 times x minus 1 squared, and then divide by -3, and we have 1/3 equals x minus 1 squared. Now we can square root both sides, and we have plus or minus square root of 1/3 equals x minus 1. And add 1, and we have x equals plus or minus square root of 1/3 plus 1. Now the square root of 1/3 is right around 0.6, so this is plus or minus 0.6 plus 1. So I'm going to say approximately. So 0.6 plus 1 is 1.6. Negative 0.6 plus 1 is 0.4. So those will be our two x-intercepts. Now the graph the vertex was 1, 1. The y-intercept was -2, and we could use symmetry to reflect that point over to here. And then we had 1.6 as an x-intercept and 0.4 as an x-intercept. And that would be our graph. Domain is all real numbers. Range, if we look at where this vertex is, the y value of that vertex is 1, and the graph faces upside down. So the range goes up to 1 and down to -infinity. So the way you would write that in interval is you always have the smaller value first, and the smaller value is -infinity, and it goes up to 1. So the range is from -infinity to 1. So that is our first learning target, which was express a quadratic function in standard form. You can use this method called completing the square to express the quadratic function in standard form. Standard form is also known as vertex form, because looking at the standard form equation, we can tell immediately what the vertex is. Now, the second learning target, finding maximum and minimum values. If your intent is to graph a quadratic function, graph the parabola, then it makes sense to write the general form into standard form so you can find the vertex and find the intercepts and a few other things so you can actually produce a nice looking graph. If your intent is just to find a maximum value or a minimum value, then you may not need to do this method called completing the square. Now, first of all, maximum and minimum values, it's just the vertex. If we're talking about the maximum and minimum value of a quadratic function, then if the quadratic function, if the parabola is facing up like this, then the vertex is what's known as a minimum value. That's if the a is greater than 0. By a, I mean the value in front here. This would be the horizontal compression or horizontal stretch. If a is less than 0, that means that there's been a vertical reflection, and so the graph is facing upside down. If the parabola is facing upside down, then the vertex is what's known as a maximum value. So you're either finding a minimum or you're finding a maximum, and really all that means is find the vertex. So if your intent is just to find the vertex and you're not necessarily graphing the parabola, then finding the vertex can be done a different way. So this statement here, if you're finding the minimum or maximum value, you're just finding the vertex, or vice versa. If you find the vertex, you're finding the minimum or maximum value of a quadratic function. And there is a formula for it. There's a formula for finding the vertex. It's called the Vertex Formula. So given a quadratic function in general form, the x value of the vertex, and when I say x value, remember a vertex is a coordinate location on a graph. It has an x and a y value. So the x value of the vertex is just the opposite of b over 2a. The y value is whatever this value is, this x value, plugged back into the function. So this is a quick way of just finding the vertex. If it says find the minimum value or find the maximum value, and it's in general form, you could do what we did in this first learning target and complete the square to write it in standard form, and then you could find the vertex from standard form. But oftentimes it's faster to use this vertex formula to simply find the vertex. So as an example, we have a function here in general form. So first, just based off the equation, would this vertex be a minimum value or a maximum value? So what we look at is the a value. It's greater than 1, which means the parabola will be facing up or opening upward. So the vertex would be at the bottom of the parabola. So it would be a minimum value. This vertex is a minimum value because if we were to graph that, the parabola would be facing up, placing the vertex at the bottom of the parabola. So it's minimum. Now, second question, find the vertex. And this is where we do not necessarily need to do that complete the square to write it in standard form. We can simply use this vertex formula. So the x value of the vertex is the opposite of b divided by 2a, where this is b and this is a. So the opposite of b is the opposite of negative 12 over 2 times a. So we have positive 12 divided by 6, which is 2. So we know that the vertex is 2 comma something. So the x value is 2. We need to find the y value. And remember, the y value can be found by evaluating now the function value of f at x equals 2. So f of 2 is 3 times 2 squared minus 12 times 2 plus 1. 2 squared is 4. 4 times 3 is 12. 12 minus 24 plus 1. So that's negative 12 plus 1, negative 11. So the vertex is 2 comma negative 11. And incidentally, you can actually continue on if you did indeed need to graph, or if you needed to, for some reason, write the equation in standard form. Now that you have the vertex, you can actually go ahead and write the equation in standard form using the vertex, and it's going to have the same a value. So here we had an a value of 3, so in standard form you have the same a value. The vertex is an x value of 2, so that's x minus 2 squared, and the y value is 11, negative 11, so it's minus 11 out there at the end. So you can actually use this vertex formula to write the equation in standard form as well if you don't want to complete the square or use that method of completing the square. Okay. So we have 1 or 2 homework problems that are like this example here. We need to write the equation of a quadratic function in standard form. We've been given the vertex here, so it's very similar to what we did with this example. If we have a vertex, we are able to write the equation in standard form. But what they haven't given us is the a value. So here we don't know what the a value is, and so we can partially write the equation is standard form. Now by standard form I mean a times x minus h squared plus k. And this here, this vertex, is our h and k value. So we can have x minus -1, which is x plus 1 squared, and then our k value is 5, so plus 5. So we know that part of our standard form equation is going to be x plus 1 squared plus 5, but what we don't know is a. And that's where this other piece of information is useful. The graph passes through the point -3, -7. Now here's the problem with trying to find a with just what we have here. This equation has 3 variables. It has a as a variable, it has x as a variable, and it has f of x as a variable. You can't solve an equation for a particular variable if there's more than one variable. This one has 3. We can't solve this equation for a because it has 3 variables or 3 unknowns. But if we consider this point here as a possible x, y value, so the point -3, -7 gives us an x and a y value. And remember, f of x can be considered the same thing as y. So if we use that -3 and -7 in place of x and y, so I would place the -7 in place of y and the -3 in place of x. What that does is give us an equation with only one variable, a, and you can solve an equation with one variable if you just have one equation. So we place, again, what we did is, or what I did is I took this value here, the -3, -7, and put it in place of x and y, allowing me to solve for a. Excuse me. So if we simplify this equation here, -3 plus 1, that's -2, and the -2 squared is 4, so -7 equals 4a plus 5. Subtract 5 on both sides, and you get -12 equals 4a. Divide by 4, and you get a equals -3. So we take what we had here in this step and replace a with -3, and our final answer becomes f of x equals -3 times x plus 1 squared plus 5. And this is the equation of a quadratic function that has a vertex at -1, 5, and it passes through the point -3, -7. Okay, last learning target, and by far everyone's favorite, word problems, application problems. So there's actually a lot of applications of quadratic functions. I've chosen 2 here that are probably the most common or the more common in a Math 1050 course. So this first one here is tracking the height of a falling object in relation to time. That's a very common application of quadratic functions, tracking the height of a falling object in relation to time, or with respect to time. So we have a function given, -16t squared plus 52t. And this is modeling the height of a ball. So y is the height of the ball, and t is any time, is a time value. So at any time t, we can find the height of the ball. For example, if t was equal to 0, if both t's were equal to 0, time is 0. That means no time has elapsed. At time t equals 0, y is also 0, which means it's at ground level. So we knew that. It's thrown from ground level. And then it's thrown with initial velocity of 52 feet per second. So if we wanted to find the height of the ball after 1 second, we would just place a t equals 1. If we wanted to find the height of the ball after 5 seconds, we would just place a t equals 5. Question here is, what's the maximum height obtained by the ball? If we were to graph this, it doesn't ask us to graph this, but since it is a quadratic function and we have negative 16 in front of the t squared, which means it's going to face upside down, the parabola would look something like this. So this is the height, and this is time. So the maximum height is really just the vertex of this parabola. And that's something that's really, really important to understand when we're dealing with application problems, especially involving quadratic functions. If it says what is the maximum this, or what is the minimum that, when it says maximum or minimum and you know that we're dealing with quadratic functions, really that just means what's the vertex? What's the maximum height obtained by the ball? They're asking us to find the vertex. Okay, we need to find the maximum height obtained by the ball by finding the vertex. And so we have our function y equals negative 16t squared plus 52t. We can use the vertex formula, which is, usually it's x equals the opposite of b over 2a, but our x value or x variable has been replaced with a t variable. So I'm going to say that t equals the opposite of b over 2a, where b is 52, so negative 52 over 2 times negative 16. So this is 52 divided by 32. And then it's fine here to use a calculator to get it into a decimal because we are dealing with seconds. So 52 divided by 32 is 1.625 seconds. Now that's when it reaches its maximum height. We know that it reaches its maximum height after 1.625 seconds. That's the x value here of the vertex. What we actually need to find though is the y value because it asks for the maximum height. So now we need to evaluate this function when t equals 1.625 seconds. So we need to find out negative 16 times 1.625 squared plus 52 times 1.625. This will give us the height. And if you plug this into a calculator, you're going to get 42 and a quarter, or 42.25, and this is in feet. And I know it's in feet, and I know this was in seconds because the maximum velocity unit of measure was, or the initial velocity rather, was feet per second. And so it's 42.25 feet is the maximum height of that ball. So like I said, that's a fairly common application of quadratic functions, is tracking the height of a falling object in relation to time. Now another one here, again, this is another type that's quite common. It's called an optimization problem, really is what this one is called, because we're trying to optimize material. We're trying to find the optimum dimensions to maximize, in this case, area. So we have a rancher that has 3,200 feet of fencing. They're going to fence in a rectangular horse corral. We need to find a function that models the area of the corral in terms of the width x. And then we need to find the dimensions of the rectangle that maximize the area of the corral. So just a quick background here. The dimensions of a rectangle, when we're talking about a fixed perimeter, and that's what we have here, 3,200 feet of fencing is a fixed perimeter. So if we have a fixed perimeter, we can change the dimensions of the rectangle to get different dimensions using that fixed perimeter and that's going to give us different areas. To maybe illustrate before we get into this particular problem, let's simplify instead that we have a perimeter. We have a fixed perimeter of 32 feet. What kind of rectangles can we make with that fixed perimeter of 32 feet? Well, we could have, let's say we had 10 feet, 10 feet, And so that would be 20 feet. So that would leave 12. So then we could have 6 and 6. So there's a rectangle that has a perimeter of 32 feet. And its area is 60 feet squared. But if we change the dimensions using the same perimeter, so let's say that we had only 8 feet here, so that's leaving 8 feet here and here. So it's the same perimeter of 32 feet, but it gives us a square, or an area of 64 feet squared. So by using the same available fencing, I've changed the dimensions so that I get a larger area. And the question is, what would be the optimum dimensions to maximize the area using a given amount of fencing? And that's what we're getting at here with this problem. So we have a perimeter of 3,200 feet. What we need to make is some kind of a rectangle using that perimeter that's going to give us maximum area. Now, the area of a rectangle is the length, or the width. We'll call this the width. And then we have the length here. And really doesn't matter which one you call length and width, but here it says in terms of the width x. So I'm going to call width x right here. So the area is our width times the length. And this brings us the same problem we were talking about a little bit earlier, that we have a function here, or we have an equation with two variables, x and y, and we don't like dealing with equations or functions that have two different variables. So what we use is the fact here that the perimeter of a rectangle is adding up all four sides. So if we added up all four sides, we'd be adding up 2x lengths and 2y lengths. So the perimeter of a rectangle is 2x plus 2y. This gives us an equation for the perimeter, but they didn't ask for a function that models perimeter. They asked for a function that models area. So why are we talking about perimeter? Well, we can take this equation and substitute into this equation to eliminate one of the variables. What I mean by that is if I rearrange this equation and solved it for y, so I could say that 2y equals 3,200 minus 2x. I didn't write that very neatly. Here we go, minus 2x, there we go. And then if I divide by 2, I get y equals 1,600 minus x. So I've taken the perimeter equation and solved it for y. In so doing, I know that if this y equals 1,600 minus x, that y also equals 1,600 minus x, because we're talking about the same y variable, so it has to have the same value in both equations. So if I make a substitution now, I could say that area equals x multiplied, instead of y, I can say it's multiplied by 1,600 minus x. And then I have a function for area that's a quadratic, negative x squared plus 1,600 x. And the importance of it being a quadratic function, especially one that opens upside down, I know it opens upside down because there's a negative in front of that x squared. The importance of that is find the dimensions of a rectangle that maximizes the area of the corral. Well, there's that key word there again, find the maximum. And if we consider what the graph of this would look like, it's an upside down parabola because of that negative x squared. So the vertex is a maximum. So again, what they're asking us here to find was what is the maximum of this quadratic function? What is the vertex? So we just need to find the vertex. So the vertex formula, the x value is the opposite of b over 2a. The opposite of b is negative 1600. And then 2 times a is 2 times negative 1. So we have 1600 divided by 2, which is 800. And x is the width of this rectangle. And the dimensions here are given in terms of feet because the perimeter was given in terms of feet. So this represents 800 feet. So we know that the width of our rectangle is going to be 800 feet. Now the y value, or the length, we can get from this equation here. Y is equal to 1600 minus x, and we know that x is 800, so y is 1600 minus 800, which is 800. So the width is 800, the length is 800. That's the dimensions of a rectangle that's going to give us our maximum area, and we know that it's the maximum area because we graphed this parabola and we found the vertex, which gives us an x value, which is the width, and the y value there would have been the area. So this proves that this is the maximum area because what we found is the vertex, which is the maximum value of that quadratic function. So the answer here, find the dimensions of the rectangle that maximizes the area of the corral. Its length equals 800 and x equals 800. So those are two examples of applications that are very, very common dealing with quadratic functions. So to review, we first talked about writing a quadratic function in standard form by this method here called completing the square. We had a function in general form, and we completed the square by moving this constant to the left and adding in a new value that formed a perfect square trinomial, allowing us to write it in factored form here, and then we had a quadratic function in standard form which gave us the vertex. Second learning target was just simply finding the vertex without completing the square, finding the minimum or maximum value using this vertex formula is a quicker way sometimes to finding the vertex if you just want to find the vertex and not necessarily write this function in standard form. But you can also, once you have the vertex, like right here, once you have the vertex, you can write a function in standard form using the vertex if you have the a value. And that's what we did with this example, is we had a vertex, we didn't have the a value, but we used that other point to plug in for x and y to find that a value. And then last thing here was solving our application problems, and the key here to these application problems is first we knew it dealt with quadratics, and they're asking us to find a maximum, and they could have also used the phrase minimum. When we're dealing with minimum and maximum of quadratic functions, really all they're asking about is the vertex.